you can take it away.
Thank you. Can you hear me all right?
Yes.
Thank you. I'm going to share my screen. Here we go. And can you see my screen?
Yep.
Okay. So thank you very much for this beautiful introduction. My name is Oscar, and the presentation today is titled, "Where does machine learning lie within the field of health data science?" Welcome everyone, and thank you for coming here today and to listen to me. I'm thrilled to be here, so thank you also for the invitation. Just a bit about myself, because usually I'm a bit nervous with presentations, so I tend to start with myself just because of that. I'm originally from Madrid, a city that is in the center of Spain. If you haven't been there, I highly recommend it. It's a very beautiful city. I'm a telecommunications engineer, and I did my studies in Madrid, and then I finished in Sweden in a little town called Lund. Very beautiful town. And then my trip or my journey with machine learning started really with my PhD. I did a PhD in computer science in the area of tracking and humans in videos and trying to see what they were doing. So human activity recognition. So just about this talk, the main topic of what we are going to take away today, I hope, is just a brief introduction to machine learning. And the way that we are going to do this is I'm going to start with some applications of machine learning applications that we do here at the Center for Big Data Research in Health at UNSW. Then through all these applications, we will try to condensate everything in the concept of machine learning. And then I will explain a bit the workflow, because it's not just to apply an algorithm blindly, but it's a bit more about how to think about the data and the research question. And finally, I will give a very, very, very brief introduction to how to start if you are new to this field. So what I'm hoping today is for you to, I want to plant this little seed that, about this beautiful world of machine learning. And in the future, feel free to contact me, or maybe in the future I will present more here. We can do this journey together and make the seed grow. So as I said, some of the applications that we do here, the Center for Big Data Research in Health. The first one that I'm going to start with is blood glucose prediction in ICU, in intensive care. So the main aim of this application is to predict or to forecast the distribution of blood glucose that a patient is going to have at a certain time in ICU. And for that, we are going to account with all the data that is in the electronic medical record. So I'm going to introduce this concept because I'm going to use it throughout this presentation. So basically, when a patient arrives in hospital or is admitted to hospital, this is what we call an episode. And then you are in hospital, and while you are here, everything that happens to you, every treatment that you go or that undergoes, is recorded in what we call the electronic medical record. So any lab test that you have, from the orders to the results, X-rays, any activity that a nurse or even a priest, if you are praying or something like that, is recorded in the electronic medical record. And moreover, if you have to go, unfortunately, to ICU, imagine all these machines that you have connected to you. So you have much more data of your blood glucose levels, of your heart rate, of all these signals. So all of this is recorded in a digital format in the electronic medical record. And this is an amazing source of data that we use in order to pursue the aims of our applications, and in this case, the blood glucose control. And then hopefully everyone gets recovered, they go home, And this is what we call a discharge. So all of this is an episode of care. And even if you think that when you go to ICU or the blood glucose is something that it seems very trivial, there's not an agreement of how to treat these patients. When you ask a doctor from one hospital, there is a way of doing things, and in another hospital, there is another way of doing things. What is clear is just that in most hospitals, they use insulin in order to treat these patients, but there are many other factors that you have to take into account, from everything that the patient is eating, that in the case of ICU is usually through IV or parental feeding, or also the status if a patient is diabetic or not. So in this application, taking into account or having all this electronic medical record data, we try to solve this problem. And then from the machine learning point of view, or from the mathematical, if you want, point of view, we had to always take a step back in order to first understand our question very well, but also thinking, okay, when we have this electronic medical record, how do the data look like? And then one of the things that we have to take into account is, like, let's say that we are a patient, that we are in ICU, and all the measures that they are taking of our blood glucose levels usually is not something that happens every hour or every half an hour, like, punctually. Maybe that's the protocol, but, maybe the nurses are very busy, maybe something happens. So what we have as a result is just usually irregular time series. And think about everything that happens to hospital is a bit like that, because you have an X-ray one day in the morning, the next time 3 hours later in the afternoon, but maybe you don't need an X-ray next day. So I hope you get the idea. Then this is translated in terms of tabular data, that we have very sparse data. So if we have a row, let's say, that is X-ray, we have maybe one, maybe none, while we are in hospital. Also, we have many variables for what I said to you, that everything is recorded in the EMR, electronic medical record. And then a very important thing, and is just that we have structured data or tabular data, as I said to you, but also we have unstructured data. And by unstructured, I mean that we have a lot of text, images, and all the signals that I was telling you while we were in ICU. So in this particular project, we use machine learning to predict the blood glucose levels from the admission to ICU all over to the discharge from this ICU with 95% prediction intervals. So this is the red dots that you see here are the actual observations. And as we just discussed, they are not regular, so they happen at irregular times. And this is the predictions, or these are the predictions that our algorithm produce. So in the x-axis, we have time in hours from admission to ICU. And here in the y-axis, we have blood glucose in milligrams per deciliter, which is one of the units. So it's, the variables, so some of the variables that we used previous blood glucose measures. We use all the nutritional and insulin inputs, if the patient is diabetic or not, age, weight, height, and many other variables. And the model that we use, I'm going just to say the name, but I'm not going to go into any detail at all, is ODLSTM. It stands for Ordinary Differential Equations on Long Short-Term Memory, which is some recurrent neural network. This is another slide, so you can see the different predictions for different patients. So each of these squares are different patients. And this project has been developed by or done by my colleague, Oshin Fitzgerald. So if you want to have, or if you like to read a bit more, we published a paper in JAMIA. And then the second one that is under revision I hope will be published soon. So we are in the second round of revision now. Then let's go back to our electronic medical record. And I think during the presentation, I will say EMR. I'm going to control the time a bit. I will say EMR. So as we said, we have the structured data. So we have our our tabular data, but we have a lot of unstructured data. And now let's go on to pay attention to the discharge summary. The discharge summary happens at the very end of our admission in hospital. So if we go back to our hospital episode, just when the people go home, they are discharged from hospital, the clinician produces a piece of paper that now is in PDF or in any other format, in which it tells that person tells everything that happened to the patient during this admission, and even some recommendations of what that patient has to do in terms of medications or care while they are at home after hospital admission. So if you want to see some examples of discharge summary, I will pass you this presentation later. So you can go to these links that they are provided by the Australian Digital Health Agency. And these are examples of discharge summaries that they are uploaded to My Health Record that every Australian has after they have been discharged from hospital. So what happens if we want to use these discharge summaries for secondary use, for example, for research? That's what I mean by secondary use. Well, nowadays we can't, because these discharge summaries, they haven't been de-identified. And as you know, it's critical and very important thing to do when we deal with health data to maintain or to keep the privacy of patients, but not even patients, also the doctors and nurses that work in hospital. So in this second project that I'm going to present, one of the local health districts here, local health districts in Sydney, had this problem. So they had a discharge summary, and the one that I have here is one that my colleague Labo wrote himself based on the structure of discharge summary. So usually we have here some structure like the header, in which you have patient and the name of the patient, some random identifiers, date of birth, who is the author of this discharge summary. In this case is Brian or George Brian, I guess it says an intern. And then here some text. It says, okay, thank you for the care of the patient, blah, blah, blah. But as you can see, there are some private information. And sometimes in some of the discharge summaries, what we've seen is like even the name of the partner or the carer. So all this information that we want to remove if we are going to use this for research or for other purposes that are not the primary purpose, we have to remove them. And these entities in the jargon are called, this field are called personally identifiable information, or PII. So as Labo said here, the PII has to be removed before we can use the discharge summary for extracting value, in this case, research. And then so we have to identify this automatically. And this is our second project that we did using machine learning in the center. And then we want to see something like that. So at the end, where it said here, patient label, or here, thank you for the care of label, where we want to see something like name, phone number, address, or date of birth. So basically, something like this. What Labo did is just to take as an input the discharge summaries, convert this from PDF to plain text. We had to do a lot of work or data wrangling with the data to convert it in something that the neural network could read. Then here there is a machine learning model that I'm going to give you the name now. And then at the end, we have to produce something like this. And then Labo went a bit further, and what he did was a system that he created the whole web application, so it's easy for everyone to use. And what he created also, I think you can here, basically you can see, you can put your username, and then you see the different discharge summaries. Not only, I mean, he created this web application for people that are going to de-identify discharge summaries. So usually in machine learning, many of the algorithms, and especially these algorithms that are classification or name entity recognition, previously to have the algorithm learning, you have to tell the algorithm what the algorithm has to learn. It's what we call supervised learning, because we have to give labeled data to the algorithm. So this application helps the people in hospital to label all these private entities that we want to remove. And the very cool thing that Labo did is that he trained his system, and now this system that he trained for a purpose of discharge summaries directly tries to predict what labels are going to be or have to be removed. So it helps to the person, to the annotators. And if he makes a mistake, the annotators just have to say, okay, this is wrong. So this is just to create these labels that will help the machine learning algorithm to learn how to remove these labels. And another thing that I want to raise here is just that, for example, if you think of from the point of view of how the machine learns what is a personal identifier, if we go back to the discharge summary, in this case we selected one with many personal identifiers, but usually what we have is a long text and just some personal identifiers that we have to remove. So this means that when we give this as an input to the algorithm, it's going to be a fairly imbalanced data set, in the sense that it's going to see many words that are just not personal identifiers, and just some, but just 10% or 5% that the algorithm has to identify to remove, as personal identifiers to remove. And if you can think as a machine, that I don't know how to do that, but anyway, I'm trying to think as a machine, you know, like if I have many things that are normal, nothing to remove, and it's very difficult, you know, to build algorithms that are going to identify only 1%, 2%, or 3% of words that are words to remove. And this is what we called imbalanced data set. So then he created a machine learning algorithm that combined the training, or helped the machine first to learn with balanced data sets. So what he did is just to remove, like if, for example, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 words that have to be removed. He just selected also 9 words that don't have to be removed. So the data set was balanced. And also he created some algorithms with just the data as it is, with imbalanced data sets. And then he combined the best answers, to put it that way. This is what we called in machine learning ensemble algorithms, because you can create as many as you want, and then, you know, see which one gives you the best answer, and then choose that answer. So currently, this paper is in archive, but we submitted to JBI, and it's been in JBI for almost a year, but we hope it's going to be published soon. And the very nice thing is that the system is being used currently by the Australian Digital Health Agency, precisely the agency that has my health record. And they are trying to adapt the system to de-identify all the discharge summaries that we have in my health record, and also used by the Australian Institute of Health and Welfare. And also recently is being used by a project called Cardiac AI. Leave the website here, but basically it's a consortium between Southeastern Sydney Local Health District, where Prince of Wales, our hospital here, belongs to, and UNSW, and they have a lot of data of patients with cardiac diseases. And again, they have started to use this system to de-identify all the discharge summaries previous to do some research. I'm a bit conscious of time. So the third project is still related to, how are you going, by the way? Everything good? I can't see anything. Yeah. But I hope you are enjoying it. So the third project, also done or developed by my colleague Labo, is automatic diagnosis coding of discharge summary. So we continue within this part of the electronic medical record in the area of discharge summaries. And then basically, as I was saying to you before, let's repeat more or less the same story. We have patients that come to hospital, something happens to them, and everything that happens while they are in hospital is being recorded in this EMR. So as I said to you before, there are some tabular data, a lot of images, and then the patients are discharged. So once the patients are discharged, I told you just half of the story, which is the story of the patients. But then we have these people here that are called clinical coders. So what the clinical coders do is just to go through each and every single patient that has been admitted to hospital, and it goes through this episode of care from admission to discharge, and everything that happens to you is going to be coded, okay, with some codes that look like this: B97.2, 13382, that are international codes that describe the diagnosis and the procedures that have been done to you during that hospitalization. And let's go into unpack this a bit, because so let's say, what was the name of the code? B97.2. As I said, this is an international code. So as you can see here, you can leave here the website where you can find these little things. This is COVID. So it's a new code, because we didn't have COVID 2 years ago. And then if we go to 13,382, you go to this website. This is then you need a ventilator, basically, and this patient was in ICU. So basically, clinical coding is the process of extracting information from all the data. Mostly they start with the discharge summary, and then they trace back to the EMR for everything that happens to you, in order to come up, with this standard international codes, which are called ICD, International Classification of Diseases. And in Australia, we use ICD-10, which is the 10th version. We are going to move soon to version 11. And I think the only country in the world that is in version 9, as far as I'm concerned, is the US, but the rest of the world, we are all in 10. So as you can imagine, these people, these clinical coders, it's a very difficult job, in my opinion, and it's very time consuming, because you have to go into the detail of the admission. It's costly, because it's a lot of time, and it's very labor intensive, so that's why it's costly. And one of the things that we learned when we started doing this project is just that these coders are in high demand, and if you go, for example, to work to one of the local health districts, they train you, and what happens is just that they move a lot, and it's a pity, because you train a person and then it goes, I mean, it's life, but in a way, there is a need to have some kind of machine learning method that, I'm not going to say that replace these coders, and this is something that is interesting, and we can have the discussion later, but helps the coders to code. So some kind of automated clinical coding. And then that brings me to another aspect of machine learning practitioners, especially in the area of health, because I'm not a clinician, I'm not a clinical coder, I don't understand any of these things. So the first thing I think, that we have to do is always to understand our question very clearly. And then when we started doing this project, we had to understand first what a clinical coder was, So then we had to go. We went visiting some clinical coders in Sydney local health district that they are close to RPA. And then one of the clinical coders, she was really nice to let us see how she works. And then we understand a bit more of how this works. For example, I just created this before the presentation. So with every episode of care, they have all the discharge summaries in the EMR, but also all the other information. And then this is when the clinical coding happens. And in my mind, because I always work with ICD-10, since I am working in the area of health, and you have all these diagnosis codes, of course, in my mind, everything is done, for researchers. It's like, oh, we have the clinical, this international code, so we can do research, and we can do beautiful machine learning algorithms and beautiful logistic regressions and things like that. But no, that's not the reason why this happens. Mostly happens because they needed these international codes for billing. So the hospitals are run by the states and the money comes from the Commonwealth. So they need to charge the Commonwealth or New South Wales Health. I think, I don't know how it goes in terms of sequence, but basically they need to charge the money for the services that they have provided. So then, for example, if you have a surgery, let's say that is a knee replacement or something like that, there is a cost. But what we learned, for example, is just that with these surgeries, some of them are done with a machine that is very expensive. So then it's very important to capture these things. And many other times when the admission has already reached some kind of level that is the maximum of money that they can claim, it's not so important to continue coding. So all these little things that we didn't know is what we learned when we went there and attended this session. So basically, with this knowledge and using the discharge summaries that were previously de-identified, we created this system to basically give as an input the discharge summaries, and then to come up with a series of diagnosis and procedure codes. This is a work still in progress, so we have done a bit, but we haven't finished. And what Labor did, and I really like this, he used technology that is called attention. So basically, many of the machine learning algorithms are black boxes. And in the health domain, you might understand that this is not sometimes desirable, because you want to know why the machine is telling you this and not other thing. So in this case, this is part of this chart summary. The machine produced 3 codes: congestive heart failure, coronary arteriography, and I don't even know how to pronounce this, acidosis. So then it's telling you, for example, with the why acidosis. So and here is orange. And if the clinical coder in this case has a question or doubt or said, oh, I'm not sure that patient had acidosis. So that person goes to this part of the discharge summary and it's like, oh, metabolic acidosis according to la, la, la. So now the machine did it correctly. So this paper also has been submitted to the Journal of Bioinformatics, but Labor already published it in archive. So this is the preprint if you want to read it. And then again, understanding the task and as a machine learning practitioner, we have to think of how many of these codes, of these international codes that I'm telling you, how many are there? Well, there are many, I mean, more than 2,000. So it's going to be a problem of a strict multi-level classification, which is, from the algorithm or the algorithmic point of view, there are many labels. So this is one of the things that we are trying to overcome now, like the many labels that we have, but also it's a very imbalanced data set, because as you can imagine, there are many patients that have, let's say, the most common diseases or the most common events like heart attack, stroke, but all the rare diseases, maybe they are not in the system. So then it's not going to, the system is not going to learn, because again, as a machine is like a little kid. It has to have examples well, it's more difficult because a kid with one example learns probably. The machine needs many examples. And then this brings me to this slide, that machine learning sometimes is not just the fancy techniques, which is great to have fancy techniques, but it's also about data. And I think it's important that we step back sometimes and we think about data, because sometimes we talk all the time about data and big data, and it's not about big data. It's about quality data. And if I tell you that, for example, with this electronic medical record, we have more and more records, but all of them are from the same disease of heart attack. Well, maybe with 1 million, the machine has already learned what a heart attack is. But maybe what we need is more records of those that are, very rare, and we don't have many records. So maybe the focus has to shift from big data to good data. And that's something that I'm very interested in. Sorry for that. And I think we have to really think of it. It's very important that the data that we are using has enough variety for the algorithm to learn what you want the algorithm to learn. And again, I invite you to read this article from the Spectrum from Andrew Nunn. Andrew, I don't know if you know him. Well, I know him personally, but he is excellent. He's always such a good communicator. And just in these lines of lack of data or of examples, this is an initiative that two of my colleagues here at CBDRH, Sebastiano Barbieri and Nick Guo, are doing. It's called the Health AI Gym. And what they are doing is, because data is a very scarce resource, they are creating synthetic data sets that you don't have the problem of, you don't have the problem of privacy or any other things, because everything is synthetic. So I invite you to, and they created these data sets using also machine learning techniques. And then it's very important also that in machine learning, always we always divide the data at least in two parts: the training and the test set. And the training set and the test set is, well, when we divide this randomly, the test set is always, we hide it and we don't see it. The machine doesn't see the test set. So the test set is to replicate in a way the future of what the machine is going to encounter in the future. So the variety of data, so the training set, is what we use for the machine to learn. So if, as you can imagine, if, for example, we have only 2 examples of rare diseases, for example, and we have to put 1 in the training set and 1 in the test set, instead of 2, we have only 1. So that's why it's so important to have this quality data. And I had another example here, but I think we are running out of time to then later to have a discussion. So I'm going to just pass this. And I'm going just to go to the concept. Now let's go into step back and let's go into think of what we learn in terms of machine learning. And I'm going to go back to the first example of a successful application of machine learning, that it was the span filter. So with the span filter, you have to basically get rid of all the unwanted emails. And then you have, a training example in which you teach the machine how to do that. And as I said to you before, you test in what is the test set that we have put apart and see how well it works. Just as a curiosity, spam is, I look it up in the dictionary, and the origin is from a sketch of the Monty Python. I was very surprised. So anyway, I leave this here. And then, in order to tackle this problem of the span, 2 things that you can do, or 2 schools of thought that we have, is one school of thought that is called symbolic artificial intelligence, and another one that is called machine learning. I'm going with the first one first. So the first one, the symbolic AI, uses rules of the type of, if the title of the email has Prince of Nigeria, then this is a spam. As you can imagine, you have people here that they have to understand the aim, but then you have to code all the rules. If the body has inheritance of $1 million, then da da da. So what happens with this way of solving problems is just that the moment a person that is sending a spam email says or watches or observes that if I say Princess of Nigeria, this is going to be a spam, is going to change to Prince of, let's say, Spain, my country, Prince of Spain. So then these people have to update the system all the time. So this became very apparent that is a very costly way of making a machine learn, because it's very hard to maintain, basically, and there is a lot of human input involved. I'm not saying that it's not used, by the way, because it could be successfully used for some things, and nowadays I think it's a perfect combination with machine learning. In machine learning, which is the aim of this talk, is the paradigm is a bit different. So where we aim is to have a model, a mathematical model, that directly learns these rules that here were hard coded, in a way is going to learn, depending on the model that we are using in machine learning, is going to learn what a spam email is versus not a spam. And it's learning this by example. As I was telling you before, we have to label the data before, which that's very costly as well in terms of human labor. But you don't have to label many usually, because the machine can learn, well, in this case. In other cases, you have to label a lot. And finally, what we have is an algorithm that has learned this data. Sorry, this model to differentiate spam versus not spam. And what is even cooler is just that before, in this approach, you have to code again the rules. Remember, if Nigeria changed, you have to put Spain, for example, then the next one will be Poland, the Prince of Poland. So then, what is very cool here is just that you can automate this, because also the spam emails change in the machine learning approach. But then what you have to do, you can automate this process of the algorithm learning what is spam versus not spam. So in a way, it's much easy to maintain. So machine learning is good for solutions that require a lot of fine-tuning or long list of rules, for complex problems that they don't even have, a solution in this form, for fluctuating environments, and also to getting some insights about complex problems. The perfect example was these discharge summaries. Some of the challenges, well, data. Sometimes for some applications we need a lot of data, and data is precious. Other times we don't have representative, or the data that we have is not representative enough for the algorithm to learn. So the quality is poor, and also it's not representative. By poor quality, I mean something different. Sometimes we have data, but we have many missings. It's not correctly recorded, or we have irrelevant features or variables. And also sometimes the system can learn very well to overfit the training data, and doesn't generalize well to test data. And just to finish this, I mean, all of you probably are statisticians. So why this machine learning field all of a sudden, I don't know, is so different from statistics? I don't want to establish this distinction so abruptly and as so many people do, but basically, I think the idea is just that it comes from statisticians in the past have been focused mostly on explanatory models. So the area of prediction, for example, was a bit unattended, but also this school of thought that wanted to replicate the human brain. So first with Charles Babbage, that it was the first person that had the idea of creating a machine to do something that it was like a calculator, the analytical machine. And thanks to people like Ada, that Ada had the brilliant idea to say she's considered, I guess, the first programmer, because she had the idea of creating a language that is abstract in order to give orders to a machine. And then in the 1940s, people like Alan Turing, that was so interested in creating machines that can think and can have a conversation with humans, or John von Neumann, that was the first person that created a computer. So from how we make or how we replicate a human brain that for Alan Turing was going to be solved in the 1950s, according to him, is something very difficult. So then I'm not going to go here, but there were two schools of thoughts. There are the blue one here and the orange one. So the blue one is the one that I called before rules of symbolic AI. And they were trying to replicate this human mind by creating these complicated rules. And it was very common till, I guess, till the 90s. And then the orange one is the one of how we make machines learn by mathematical models. That is the orange one, and that is machine learning. And initially, the aim was very broad, was just to replicate this human mind. But now what we have been able to do is to do little tasks. Like, for example, this task that I have described to you today. And the machine so far is very good to, let's say, predict the blood glucose levels, that machine, and then we train another one for coding the discharge summaries. But still, they are just narrow task. So if you put the same algorithm that you train to de-identify the discharge summary and you try to predict blood glucose, it could be good or it could be bad, but chances are that it's very bad. And then just to finish off, just to say that when we say machine learning is, or my understanding, is just machine learning is just a name that describes techniques that we use to solve a problem. And then you might call it a statistics, you might call it a statistical learning, I might call it machine learning, but in a way, what is very important is to have clear what is your aim. So if your aim is description, your question is like something on along the lines, how can women, for example, age 62 years old with a stroke history be partitioned in classes defined by the characteristics? So you can do this with, I don't know, any data wrangling. And in machine learning, for example, we can do cluster analysis. Prediction, like what is the probability of having a stroke next year? So then you can do it with a simple regression, but you can use many machine learning techniques like decision trees, random forests, SVMs, neural networks, then causal inference, and then one that is reinforcement learning. That is one of the areas that I think is more machine learning like it's like how, for example, how can we find the best dynamic treatment over time? You know, how the system can tell, for example, what is the best treatment at each point in time for a patient to have. And I don't know if this is very similar to causal inference. I still have to think of that, but this reinforcement learning area is an area that I think is going to grow a lot. And because I'm running out of time, I think we are going to leave it here. And just to say that based on these questions that I showed before, we call the techniques usually unsupervised, that you can see it fits here in the description. When it's prediction, we call it supervised learning, and then reinforcement learning. And then what I have been going through all this presentation, and this is something that I always try to tell my students, it's just that we have to have clear the whole pipeline of machine learning, from the research question to do we have the data to answer this question, to the data gathering part, exploratory data analysis, and then just the plugging of the algorithm is just here, you know. But it's very important to have this clear and to do it well, you know. And then if you want to start with this world, I recommend this library, this Python library, scikit-learn. And then for you to have everything, you don't have to install anything in your computer. No Python, you can use Google Colab or Collaboratory that has everything installed already, and you can use, you can code online. And that's all. I think I went a bit over time. I hope you enjoyed it. I'm happy to have any questions. So thank you.
Thank you so much. That was really great. We do have one question in chat. I encourage anyone to put a question in chat or unmute at an appropriate time. But Sarah asked, given, I think this is regarding the project of helping coders, Given that the codes are being entered primarily for billing rather than clinical care, how accurate are they? And do the high bill rate codes get used more when there are a couple that could be used? And she's just put her camera on, so she may have something else to add.
No, that's fine. I just thought it could be a really interesting side analysis, and it could both disturb your data, but it could also be a research question of its own, I guess.
I think you are right, and I'm not sure, in all honesty. I think if they are mostly used for billing purposes, I think some of them might not be, recorded if it's not, they don't provide enough data. I know that, for example, in the past, they used to record many codes, like, for example, diabetic. If you were diabetic, even if your episode of care didn't have anything to do with diabetes, they changed that protocol now, and they only stick to the ones that then you receive treatment for. So having said that, yes, I think there is a lot of potential to see that. Did I answer your question, Sarah?
Yes, thanks.
Leonard, go ahead. Unmute yourself.
Thank you. Hi, Oscar. Thanks for the nice talk. I was wondering about the unstructured electronic medical records. Are you working on models to automatically extract variables of interest as well? Would that be a way to make that task easier?
Yes, we are, because with every task that we do, we have to select the variables of interest, if that's your question. So what specifically do you have in mind?
So I guess the way I understood the vignette was it was more about the identification part, so that any sensitive data would be redacted, basically. But if there's, for a study, particular variables that you're interested in, say, I don't know, blood pressure, severity of certain symptoms, whatever is of interest, rather than having someone to manually go through all the text, if you're working on models that can sort of simplify that task.
In the case of text models, we give all the input. We give all the discharge summary in the imbalance data set, to put it away. So we don't select any paragraph, or if you refer, for example, to if there is a page that there is with the results of the lab test, probably go to the lab tests that are more relevant. No, we don't do that. We allow the machine to learn, which is what machine learning in this case is. Having said that, some of the discharge summaries were so long that they don't fit. I mean, the length of the input was, we had to, how do you say, cut them. So potentially what Leibo did is just that he realized that some of the most important information was in a paragraph called, I don't remember the title of the paragraph. So he divided the discharge summary into chunks, and then he put this chunk at the very beginning, because the machine, is not like us that has to read sequentially. And then we had to cut the discharge summary. We cut in areas that we thought they were not relevant. That's with the text. With the other application, for example, the blood glucose prediction, yes, we did variable selection and variable importance. So there are so many variables. So we selected the ones that were more correlated with the output, and they were more relevant.
Makes sense. Thank you.
Okay, there's another question in chat from Tommy. He says, for name tag recognition, could you please tell how much data you need to develop the model? Tommy, it might be good for voice if we need clarification.
So yeah, what is name tag recognition?
I'm assuming this has to do with the coding again, or the de-identification. Sorry, I think that's what he's talking about.
So for the de-identification, how how many data you need to develop the model. In this case, because the labeling, we had to label manually the discharge summaries. I think we labeled 500, if I remember correctly. So what we did is like label, and another person independently labeled the discharge summary. So all these personal information words, and then I was I don't know how to call it, the resolver. If there was a conflict, I had to check the discharge summary and decide. So in this case, there were 500. In the project of the ICD code, so the diagnosis code, I think there were 8,000 so far. But so far, we have just coded the 15 most common diagnoses. And now Label is developing the second part for multi-label. And I don't know how many discharge summaries we will use for that yet. Did I answer your question?
I think you did. I think we identified the right thing that he was talking about. So
okay.
Yeah, I think you did. Are there any other questions from anyone out there?
Or comments?
Or comments, yeah. No, okay. Oscar, thank you so much for joining us. We're going to make the video available on our website, and we have a couple of requests for PDFs of the slides, if that's possible.
Yes.
If not, I think they're particularly interested in the links, so that would be really great. We can post those as well, if that's okay. Thank you so much, Oscar. It was a really great talk.
Thank you. So I will send, Nancy, I will send you the presentation, and then you can distribute it. Is that okay?
That's perfect.
Okay. Thank you, everyone. I really enjoyed it. So thank you.
Thank you very much.
Bye.